members and with Advanced Functional Fabrics of America, as well as United States Army Corps of Engineers Construction Engineering Research Lab for their support and expertise throughout the research project. Without these partners, our project would not be possible, so thank you. Today, I'm joined by an incredible team, Cadet Nichols Parker, who was the lead in our concrete design as well as the testing procedures, Cadet Bren, who was leading our culvert design and advanced materials section, and of course Cadet Leslie Thompson, who was leading our 3D printing and mechanical engineering design process, which was the backbone of our project. And of course, I would like to recognize our advisor, Dr. Judge Panos, for his expertise and mentorship throughout the project. So what have we been working so far? Based on various meetings with our technical partners and stakeholders, we came up with a problem statement that you can see on the slide. Our goal since the day one was to develop a concrete mix, including the advanced materials such as hydrophobic pristine graphene, which we would later use to 3D print with advanced concrete manufacturing the concrete culverts. These culverts was meant to be easily to deploy, user-friendly, environmentally friendly, and durable. Our project was split into two halves. Phase one was focusing on ASTM C109 test, compressor strengths of our specimen. Moving on to phase two, with the chosen design from phase one, we were gonna 3D print the concrete culverts and test them for tensile strength. Today, we're excited to share the findings that we came up with throughout our project. And without further ado, I would like to hand it over to Cadet Leslie Thompson, who can walk us through the mechanical engineering design process. Leslie?
So we start off the mechanical engineering design process by figuring out who our customer is. Our customer is the United States Army, more specifically United States Army Corps of Engineers. We got various meetings with them to figure out what do they want from us? What do they want this concrete to do? What are their objectives? So we got a whole bunch of objectives from them, and then we decided to categorize them in this pairwise comparison, as you can see in table one. The three overarching objectives that we had, that Nick already stated in the proper definition, was durable, eco-friendly, and user-friendly. Then from there, we compared those objectives to each other in figure one to find out what's our main focus, right? What's the main objective? So we look towards the relative importance column, we see that durable is our main focus for the project, with an emphasis on structural strength. Next slide. So moving on towards the conceptual design from our definition part of the mechanical engineering design process, we needed characteristics, which Nick Parker can go over the characteristics.
Good morning, everyone. Once again, Nick Parker, concrete mix and testing lead. And so really what I want to talk about is the upper figure, where we basically wanted to quantify the characteristics that would encompass the scope of our project. So once again, we talked about durability, user-friendliness, and then sustainability ultimately of our concrete. But there's no way to do that without quantifying the relative importance of different things. And so in this table, you'll notice things like material quantities, you'll notice the test results, and the ultimate way that we're gonna design and mix our concrete. Really, we did this through plenty of iterations as most design, build, and then test projects go. And so now Leslie will kind of talk about how we use these quantifiable characteristics of our concrete to move forward with the design, planning, and ultimate solving of this problem through the mechanical engineering design process. Leslie.
So we have these characteristics, now we have to compare those characteristics to our objective. That's why we have this quantity function deployment down here, so we can get that relative importance of like what characteristic has the most significant relation. If it had the most significant relation, we gave it a 9. If it had the least significant relation, we gave it a 0. So as you can see, and the relative importance from the EDSL in the figure above, it has quantity of Portland cement is the first one, and after that we have quantity of pristine graphene.
All right, good morning everyone. Just to reintroduce myself, my name is Cadet Bren, and one of my primary functions for this project was I was the materials lead. So you're probably wondering what separates this concrete from a normal concrete, and that comes down to our two different admixtures that I have here. We obtained pristine graphene and recycled glass fibers, which I'm going to send out to pass around the audience right now, from our technical partner, Carbon Rivers. These materials were used throughout our project to help increase strength. So pristine graphene, as seen in figure 4, is a microscopic level of graphite. So imagine pencil lead, but on a 1 to 2 atom layer thick. This is a hydrophobic substance, as Nick mentioned earlier, and it's formed in a hexagonal lattice based off of the molecular compound of carbon. Because of this compound, it's very, very strong. It doesn't have a lot of loose molecular parts, and so it's very, very tough. So when used in an admixture, like concrete, it provides a lot of compressive strength. It essentially fills in the void spaces that the concrete's gonna have due to difference in aggregate sizes, wrapping around those particles and making it a more unified object. Glass fibers, throughout testing, we were able to kind of figure out that it wasn't the most feasible based off of our current mix design, and we're looking to do more research into this in the future. It was originally supposed to be added as a way to incorporate eco-friendliness. The fibers were obtained through the milling of wind turbine blades, which would have otherwise been thrown away. And they essentially act as mini rebar within the concrete and help reinforce against tensile, which is typically the weakest part of concrete.
Oh, so our alternatives, right? We had alternatives, for the first row, you can see our alternatives, the amount of pristine graphene, we talked about that in the EDSL, that was one of our characteristics. So we used the 0.011%, 0.015%, and 0.020%. We went with the 0.015%, Nick will go through that a little bit more later about why we did that due to structural strength. Then we said, all right, where are we gonna be at? Where is this concrete gonna be made? Where's it gonna be 3D printed? We said, okay, we're gonna be stationed in the Pacific Theater, so we chose Guam. Everything else, we wanted to use local materials because that's the most cost effective rather than get it shipped from the United States or Philippines. So the second row was location. Then after that, we went mix design. Mix design completely, again, Nick will go through that. We had a control mix with nothing added, just regular cement. We had PCE mix where we just used PCE and then we had PCE and graphene mix. Later, Nick will show how the PCE mix is better, PCE and pristine graphene mix is better, and the reason why we chose that. Then Brandon would go through the shape of the culvert. Shape of culvert, we had circular, we had elliptical, and we had box, and he'll go through that later.
Great, thanks, Leslie. And real quick, before I dive into ultimately our concrete mix composition, I want to give a special shout out to Mr. Mike Flower. Wherever there's concrete mix or testing, there's Mr. Mike Flower. He was extremely crucial to everything we did regarding concrete in our project. And so he deserves far more than a thank you, but I think that will do for right now. So for our concrete mix, really what we needed to figure out was the ultimately efficient and strong effective concrete for our mix and ultimately 3D printing, because one of the careful processes we had to manage with concrete is managing its viscosity and its flow, because the stiffer you make a concrete, the more resistant to 3D printing and flow it is. That's something we carefully iterated through. And as Leslie kind of mentioned, we wanted to carefully manage our quantity of pristine graphene. As we said, it aids strength, but we wanted to do so at an efficient level. We decided, and we'll show later, that at a 0.015% compared to our relative weight cement, that was our perfect and optimized concentration of cement. And finally, we'll talk about this additionally, but we were forced to remove the recycled glass fibers for the 3D printing component. So this prototype right here does have pristine graphene in it. It does not have glass fibers because of their reduction in flow. And that's something that we anticipate we can move forward with for further 3D printing. And so if we were to zoom in on our concrete roughly 10 to 20,000 times, this is what you would look like. And the thing that I really want all of us to draw our attention to are the concentrated areas of pristine graphene. So at first, they initially just reveal any sort of seam or crack. However, under a scanning electron microscope, that wouldn't appear a black void. And so instead, like you all saw with that material specimen, that is concentrations of pristine graphene where it found voids and aided in its strength. Thanks.
Thanks, Nick. Just to go back to the concepts of operation for phase one, as we mentioned, we conducted the ASTM C109 test, which is a standard compressive strength for the concrete cubes, which we use 2x2 cubes to keep it at a small scale for efficiency. We tested these cubes for a 28-day period, and we got the results on the figure on the slide. What is important is that these tests were done both by Cadet team at West Point, as well as our technical partner, Carbon Rivers. The results for Carbon Rivers shown in the blue bars, which also provided the advanced materials of pristine graphene and glass fibers to our team. Based on the remarks from our technical partner, we examined 3 different concentrations of pristine graphene, 0.011, 0.15, and 0.20%. And the testing procedure on the 4-inch testing machine at West Point is also seen on the pictures in the lab. So just to the results, we have remarkable improvement according to Carbon Rivers for pristine graphene concentration of 0.20%, which will result in 51% improvement in compressive strength with respect to the control mix, while we have 64% improvement also with respect to the control mix in compressive strengths of the concrete mix for 0.015% of crystalline graphene concentration. At the end of the day, during phase one, we decided to conclude that this 0.015% concentration would be the most optimal mix that we would proceed with during phase two of our concept of operation to 3D printed concrete culvert that you can see. Thank you.
Okay, so like Leslie Thompson talked about earlier, the process for going through a culvert was once again gone through the mechanical engineering design process. And we went through multiple different looks of box culvert, elliptical culvert, and circular culvert. We ended up deciding that the circular culvert, which we have here, was the best option as a result of the flexural and load capacity in comparison to the other shapes. But what is a culvert? So a culvert is a pipe or a tunnel which goes underneath a roadway or a railway and passes water between the two parts. During the global war on terror, we realized that IEDs or other explosives can rapidly hinder movement of units and materials just through taking out a piece of infrastructure as simple as this. That's why the goal of the project, as identified by U6, was to be able to rapidly repair these pieces of infrastructure to allow us to move on the modern government. The design of this shape was done using ASTM C14, which details the design of an unreinforced concrete circular pipe or culvert.
So if you pay attention to figure 14 is when we went to Champaign, Illinois to the USACE CERO, Construction Engineering Research Lab. So this V-hut behind us is a completely 3D printed structure, just to show that we don't only 3D print culverts, we could 3D print like actual buildings and offices, those things. Even down to the floor is 3D printed. So to the right of, to the left of it is figure 15. That's our actual culvert being printed out through, and that's how it came out the way it is, because it had to go through. I don't know if you know anything about 3D printing, but it's like 3D printing goes by one layer at a time, so they do one layer each row. That's it. That's it.
So, as we talked about earlier, our project was split into two different phases. And in phase two, one of the most crucial aspects was the testing of these 3D printed culverts that we got from CERO. During the design process, we kind of ran into an issue with how do we analyze these culverts? How do we anticipate how they're going to fail? It's a 3D printed shape, which is going to solidify at a different rate based on when it was printed. So, through analysis and speaking with Dr. Williamson, we decided that it would be best to kind of make an assumption due to many different factors and treat this as an arch. So we assumed that this would be a fixed arch, as shown in figure 16. So when we were testing these, we underwent ASTM C497, which is shown in figure 17. We were able to conclude that our assumption was supported. Based off the moment diagram in figure 16, the maximum moment would occur at the top and bottom of the arch. As you can see, based off of this image here, the failure occurred at the crown and the base of the culvert, which means that our assumption, although not proven, was supported.
Great, thanks Brandon. This slide is ultimately to show our testing results of our rupture strength from the concrete that we made in-house and the culverts that were 3D printed. The important thing to note is these are the exact same mix of concrete, which really allows us to elicit and draw out any discrepancies which would be to the constructability and strength of 3D printing. Now our p-value noted up there simply discloses that we are 94% confident that our results are statistically comparable, and we can kind of move forward with statistical analysis and analyze the differences between both our culverts and our printed concrete. Thanks.
So just to provide some final conclusions and recommendations, what we have done so far, we have seen that hydrophobic crystalline graphene advanced material has really the potential to improve the compressive strengths of the concrete mix about 60% according to our technical partner Carver Rivers. We have seen that these advanced material can be successfully incorporated into 3D printable concrete mix, while the advanced concrete manufacturing really has proven that it can provide more reliable and stronger approach compared to the traditional casting of concrete. At the end of the day, we're taking advanced materials, we're combining it with the advanced concrete manufacturing, and we see that this can really be the future of motor infrastructure, and especially important for the United States Army within its operations areas, and especially the Pacific area of operation. So with this, I would like to thank you for your time and attention, and I would like to open the floor for any questions the group might have. Thank you.
So both your results than Carbon River's results were very different. I imagine you guys spent some time trying to figure out why. Any like theories, or were you able to figure out exactly what the difference was between the processes that you both used?
Yes, sir. Thank you for the question. Absolutely. So if you want to go back to that slide. Two of the main differences that we kind of alluded to was one, this was sort of a learn as we sort of do our project, which can be very difficult with concrete, which kind of varies very quickly with any sort of addition of water or aggregate. The other thing was the controlled humidity and temperature in which our concrete was at. The opening and closing of our curing chamber in relative change in temperature likely changed our results, whereas Carbon Rivers has a very advanced humidified controlled curing environment. Thanks, sir.
Yeah.
I have a question about 3D printing. What are the requirements to 3D print from concrete?
Okay, so to 3D print concrete needs to be printable, it needs to be buildable, it needs to be extrudable, it needs to be pumpable. So if you can't print it, it's like either too wet or too dry. If it can't build on each other, like see how it's built on layers, it's gonna collapse. If you can't pump it through the nozzle, it will never get to the area it needs, and you can't extrude through the nozzle, then it also won't print. So those are the requirements.
Yeah, and to kind of add on that, you have to have a certain aggregate size based off the extruder of the nozzle. So if it's too big, like pieces of rock, it'll get clogged. And then we kind of also got into an issue with the fibers like we were talking about, where it was too thick, so it wasn't flowing through the nozzle well enough. So because of that, we had to take it out. But you need aggregate side, you need to have an appropriate slump so it doesn't collapse inwards on itself, and then you also need what Leslie was talking about.
Oh, yes, sir.
Yeah, thank you for the great presentation. My question for y'all is, were there any unforeseen challenges or issues or scenes of turbulence that you experienced in your design process?
I can take that one. So to start off, we were pretty much from a base point. It was, we have this technical partner, Carbon Rivers. We have pristine graphene and recycled glass fibers. From there, it was develop the project and figure everything out. So we weren't originally thinking culvert, but after a meeting with USACE and talking with them and what the Army actually needs, that's when we shifted over to that. And I kind of alluded to it earlier, the design of the culvert is very complicated, because if you think about how this thing's going to fail, like there's going to be pressure going through it, it's going to be under a load, there's going to be a tank, it's going to apply the load slowly at one point, there's going to be deflection, there's a lot of different things that go into it. So the design process of the culvert was like my bane of existence.
Did you consider, obviously culverts are out water beneath the roadway, did you consider seepage or like the impact that 3D printing it would have with the water going through the cracks as it was manufactured?
I can take that. So there's no gap actually, believe it or not. So it meshes together quite well. If you come down to our poster, we have one that's already broken that we broke apart, and you can see how, even though it's 3D printed layer by layer, it actually come out.
So how do these culverts compare to the culverts we typically use in terms of strength and durability?
Yes, sir, absolutely. Thank you for the question. And this is kind of part of the challenge that we faced. It's really hard to kind of test these things like in situ. Ideally, we would test this under earth, under a load, with dynamic vibrations, etc., with water flowing through it. That is a part that we acknowledge we were not necessarily able to do. And part of our project was, can we 3D print effective ground infrastructure? And so I think through our testing, anyone in this room could stand on this and it would be just fine. We could absolutely, under some earth, drive a car over it, it would be fine. Could we drive an M1 Abrams tank over it, intense flow through it? That's kind of our future research.
So this was, how can we do it? And now Searle will figure out if it's cost effective, etc.
Absolutely.
What else did you learn reference the ability to use 3D printing overseas and then deploy? So you did this particular culvert, but how else you might be able to use 3D printing as something that you have overseas?
So that B-Hub was built in 17 hours. So if we needed like an office or somewhere, somewhere to be to work out of, you could easily print that within 17 hours.
Okay, so as a mechanical engineer, did you do parts
Yes, you can do
For
parts.
sustainment,
You can do parts. You can do the geometry is not limited to these two geometries. They can do way more. It's just that we can put all the pictures up there in the studio.
On one of your last slides, you had a p-value, can you just tell me what was the hypothesis you were rejecting and what was your sample size?
Yes, sir. Thank you for your question. Our sample size was fairly small, which is where we anticipate we could have improved the sample. This is just restricted by the amount of material we had to test. Our p-value of the 0.059 is a student t-test, and really what that asked was, is our data statistically comparable, these two different sets of data, rather than just simply comparing their means to each other.
Ken Kraetzer, Cadets Media. I'm just curious on the 3D printing, how hard is it to develop the software for the printer for an item like this or any particular item?
The software? Are you
Software.
talking about like what's it called? The system?
Well,
Or
programming the
make
printer
it-
so it can print what you just produced.
Okay, so to set it up, it takes less than a day, but the software itself is already, you just need to install it on your computer. It's just like SolidWorks.
So somebody else develops the software and then you install it when you need it. Okay.
Sir?
Any thoughts on, the distant, not too distant, let's say 10-year horizon? Where do you think, from a construction standpoint, where is this 3D printing capability going? Think that it's gonna ultimately replace many of the current methods that we have out there? What are your thoughts on that? You guys have immersed yourself in this topic for a year.
Personally, I think it's gonna be more than 10 years before we really start to see this really get into the infrastructure. The machine itself for 3D printing is a large apparatus, and a lot of like fine detail pieces of concrete would probably be pretty difficult to maneuver this apparatus in to do it. I think it is definitely something where, especially in terms of like labor and conditions, it's much easier. You can run this pretty much throughout the day with various periods to like load and unload, but it kind of takes away the human element and human strength of construction. I'd say maybe 25, 30 years you could probably see it kind of really getting into the inside.
And I would add to that as well, I think this could be used in complement to traditional concrete casting. So whereas throughout the day, anyone using concrete material structures, a printer could be going overnight, building a storage shed, etc., which would not require additional labor, and that can be easily programmed into any sort of software.
Thanks.
So we got time for one more question. We didn't hit anybody back there.
I was going to ask about what the impact to aggregate quality has on the overall performance versus the addition of your pristine grafting. So you added some quantity of pristine grafting, you had a magnitude change. How does that compare to the magnitude of different preparations for the aggregate? Whether, because if you're expeditionary printing, right, you're using local aggregate, you have a wide range of what the aggregate actually is. So how are the impacts of the range of different aggregates in preparation for it compared to the impact that you get from pristine grafting?
Yes, sir. Thank you for the question. The simple answer is it's crucial. The strength of the concrete ultimately relies on the aggregate as opposed to the pristine graphene, which provides really an incremental increase in strength to an already existent quality of mix. And so, fortunately, the materials that we use that were comparable to the regional conditions that Leslie described provided us with a structurally robust concrete. However, if forced to use a weaker mix or a very poorly graded aggregate, we would suffer in terms of strength quality. So that's definitely a portion of a project that deserves plenty of attention as well.